Okay, so now what I want to do is I want to do this part of the homework problem. This part of the homework problem right here. So we're going to have whoops, that's the wrong thing. Okay, so we're going to have some integer m, and then for all of the integers from 1 to n, we're basically going to do this thing right here where we compute the number of terms in the Collatz sequence for 1 to n, take the average of that, and then divide it by n. So that's what we're going to be doing. Just because I kind of want to keep this up here. Just because I want to keep this up here to kind of go off of, I'm going to come down here and write new code. So m is equal to 10. And now I'm just going to do maybe what might be the most straightforward way, and maybe there will be better ways to do this. We will see, perhaps, as we go on. I'm going to say AR is going to be equal to np dot arange, and we're going to go from 1 to m. Okay, and again, I just want to print this to see what I get. It's going to be the numbers 1 to 9. Okay. Now let's say we actually want to go up to 10. So like we want to look at the numbers 1 through 10. I'm going to put m plus 1 here to ensure that we go up so to ensure that we get the Collatz sequence for 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, or the number of entries in a Collatz sequence. So let's just see. Okay, that's what I need here. And now I'm going to say for in range 1 to m plus 1, we're going to do something. What we're going to do is we're going to look at the number of terms in the Collatz sequence for numbers 1 to n. So I'm going to say CAR is going to be equal to VCol, so the vectorized form of Collatz. And now I'm just going to do a slice of my array. So it's going to be AR, and I want to go from the first index, which is 0, up to the n minus 1th index, which would be in here. Okay, so for example, my phone was dinging there. Okay, so for example, what's going to happen, n is going to go from 1 to 10. So range 1 to m plus 1, if m is equal to 10, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so CAR, I'm going to apply the vectorized Collatz function to the array 0 to n. Or sorry, the slice of the array going from 0 to n. So if n is equal to 1, this is 0 to 1. So if I come down here just to test this, 0 to 1, you're just going to get the number 1. So let me do print. So this is going to be an array with the first element. Okay, and then we're going to apply, in succession, we're going to apply the Collatz argument, or the Collatz, we're going to apply the, so now this is going to be an array, and what I'm going to get is going to be the number of terms in the Collatz sequence for the numbers 1 to n. Okay, so now what I want is I want the average. So I'm going to get, let's say, AVG is equal to V col, NP dot mean, NP dot mean of this, and then I will say, I don't know, I'll say divided average. D average for divided average is going to be this divided by n. I'm just going to see what happens. Looks like everything is going well here. And this is not going to be what I want to do in general, but I'm going to do this for testing at least. I'm going to print out what that is. So if I run this, I'm going to get this, which I believe is what I said it should be, right? 1.75, 1.22. Okay, that's what we have. Okay, but now what I want to do is I actually want to save this into an array. So I'm going to say AR is equal to NP dot zeros size 10. And then I'm going to say, I'm going to say the average AR. Not sure if this is the best name. And so down here, I'm going to say D average AR. Okay, now I need to be careful about what I'm doing here with the index. So n's going from 1 to n plus 1. So the index I really need to do n minus 1 because this goes from 1 to n plus 1. But like for the first item I put in there corresponding to n is equal to 1, this is really going to be the 0th indexed item. So this is going to be d average, and when I run it, looks like everything is working well there. So print d average, whoops, yeah, that's right, average AR, and I have that. Okay. And now what I want to do, once I get done with that, I want to plot this. So I'm going to do plt.plot, and I'm going to do AR and d average AR. I'm going to run this, and I'm going to see what I get. Okay, so I actually kind of like the lines for now. But I think I will not like them in just a minute. So I'm going to change this to R circles. So when we plot this, instead of lines, there's just going to be like a dot there, a dot there, a dot there, so on and so forth. Okay, so this is what we get. I don't know if I like that or with the lines. But now I want to see what happens if I run this up to 20 and run this all over again. Oh, you know what? This should be equal to m. Okay, and it definitely seems like this is going down. I wonder what happens if I do 20. Sorry, I just had 20. I wonder what happens if I do 100 and see if it looks like... Okay, so that's interesting, or maybe it's not. I have no idea if it's interesting. It definitely seems like the average is going down to 0. So let me just do 1,000, see what I get. It's going to take a while. Yeah, so it definitely looks like the average is going to 0, which kind of makes sense to me because we're dividing by n. But now I'm going to go back to 20 again. Whoops. This is just me playing around. I'm going to go back to 20 and not divide by n and see what happens. Okay, now it looks like it's increasing. So that's cool. We get some interesting patterns here. Okay, and so we have these kind of interesting stair-stepping patterns. Yeah, so that's interesting. Perhaps this is a problem that has been studied a lot. So I assume if you Googled it, you could kind of get some ideas for what's going on here. But it is interesting that we have these stair steps going on. So let's remember what's happening here. So like for 40, what we're doing is we're computing the number of terms in the Collatz sequence looking at the numbers going from 1 to 40, and the average number is around 20. And we see what's happening here. Yeah, so the average number looks like it's around 20. And that pretty much is true from about 30 onwards. The average number is 20. Then it looks like from 40 to, I don't know, maybe 50 years, something like that, the average number is somewhere between 20 and 25. So again, just now because I'm kind of doing it, this looks like maybe the graph of a log, some sort of log. If I look at maybe... the natural log, whoops, I'm doing this on my calculator, the natural log of 100 is equal to 4.6. So this maybe is a little bit more than natural log. Maybe not log, but this is like, I don't know, maybe this looks like a square root function. So probably you can even stop watching now. So let's see what happens if we go up to 500. Now, the way that I'm doing this is very inefficient, because really, like once I compute, the Collatz sequence for a certain number, higher numbers might join up to the lower number sequences, and I can use that. But I'm not using that at all. So it makes running the code very inefficient. So I'm going to run this. I'm going to pause it as it runs. Oh, that actually did not take as long as I thought it would be. So we got 500. That looks like it's about 50. So that's interesting. Here, 1,000. Okay, so I'm going to do something different now. I'm going to see what happens if I, so instead of actually graphing the array, what if I graph the log of the array? and see if I get something linear. I did some other experimenting and it didn't look like a log, so let me do this now. So if it is kind of a logarithmic relation, I should get something more or less linear. So I don't get that. Okay, what about if I do 5,000 here? This is probably going to take forever to run. Obviously, what I just said was wrong. So let me go back to 1,000. That was embarrassing. We'll just chalk that up to being the end of a long day. So let's say I do an exponential function. I'm going to do it at 1,000. Let's see what we get. If the relationship was exponential, okay, so now this makes more sense. So now the fact that it now looks basically exponential tells me that maybe it's not really a logarithmic law, but it definitely looks like it could be like a fractional power law, right? The graph of this looks like it could be, the square root of x or something like that. So if we were to do maybe like this and see what we get. Okay, so that looks more and more, well, whatever. Okay, so I could do this forever. Yeah, so my guess is that this is something that you could Google because this is a problem that has been studied for a very long time to get an idea or just think about maybe there's a reason that there's a an interesting regular pattern like this. At any rate, that's what I wanted to show you. Combining a lot of the things that we've looked at so far. That's what we have. So that's all that I want to talk about for this video, and I will see you in other videos and in the discussions.